Video today, part 8.3, simple recurrence relations. Now we need to solve recurrence relation. But when we start, we want to start with relatively simple recurrence relations. So let's start with the one we have from the Tower of Hanoi problem. Okay, so let's do the efficiency analysis. Let us count the number of basic operations. So what is the basic operation in the Tower of Hanoi problem? So very simple, right? Disk move. One disk move, we define it as the basic operation, right? So move a disk from one peg to another. We do not need to specify the pegs, so which peg to which peg, right? Just a general one peg to another. So any two selected pegs, we define, that's the basic operation. Then we define the count number function C of n. How many moves? The number of moves we need for the data size n. Then let us derive the recurrence relation. Based on the procedure, we can easily write out the recurrence relation. So why? Look at this formula. In order to represent count number for the problem size n, recall the procedure. First, we need to solve problem size n-1. So then we need to pay Cn-1, right? After that, we move the bottom largest disk to the destination peg, make it in place. So that is the one move, right? One move, just one move. After that, then move that n-1 disks back to the destination peg, repeating the whole thing of that n-1 problem another time. So 2. So we do twice. We solve that problem, subproblem, n-1 size twice. So that is the recursion formula. All right. Then the base case, if one disk size 1, you only make one move, right? One move. That's trivial. But that is our base case. C of 1 equals 1. Now we need to solve this problem. Solve the recurrence relation. This time, we need to, use some math technique. To solve this problem. Okay? The basic idea, transform the formula. If we want to solve this recurrence relation directly, for many people, it may not be that easy. But now we need to do some special transform. So then we can make, after the transform, we can make the solution easier. All right. Solve the recurrence relation. Question: how to transform the formula? So this is the most important step. How to transform the formula? Okay. All right. Here, I like to give you some commonly used method. In this question, I want to introduce this method. Explore the similarity in structure. Similarity in structure, mathematical structure. Similar mathematical structure, similarity, mathematical structure. In our original recurrence relation, we don't have it. Yeah. You can see the two sides of the equation, two sides, C of n, 2 times C of n minus 1 plus 1. You can see the expression structure at both sides are different. If the structure is different, then you cannot take advantage of the similarity. Okay, here we need to do transformation. So when we do transformation, our goal to get a similar structure. How to get? So here, let me show you one simple trick. Because plus 1, right? Right hand side, you have plus 1. Left hand side, you don't have any plus thing, right? In order to get similar structure, you also need to make the left hand side plus something. So both sides, you have plus something. The structure could be closer, right? Left hand side, right hand side, make their structure closer. Yeah. So how to make that move? Plus 1 both sides. You plus 1 both sides. So left hand side plus 1, the right hand side 1 plus 1, 2. All right, 2, it's okay, but you have 2 leading coefficient of the C function, and this 2, can you factor that 2 out? Right? After you factor that 2 out, what do you get? What new structure do you get? Comparing left-hand side and the right-hand side. You can see at the left-hand side we have C of n plus 1. At the right-hand side we have C of n minus 1 plus 1. Both plus 1. Do we get a similar structure? Yes, a similar structure. Right? We can take advantage of the structure similarity to make it simpler, to simplify the problem. Let us introduce a new function d of n. D of n represent C of n plus 1. Okay, so then at the right hand side, in the parentheses, that is the d of n minus 1. Okay, both in d function. Why we can use d function to represent both expressions? That's the reason we need a structure similarity. Otherwise, we cannot use one function to represent both expressions, right? So after that simplification, we have a new recurrence relation. This time, d of n equals 2 times d of n minus 1. Do you think it's simpler than our original one? C recurrence relation? Much simpler. Yeah. How to solve it? All right, so let's do it. Initial condition d of 1 equals 2 because C of 1 plus 1. 1 plus 1, 2. So d of 1 equals 2. Yeah. Then d of n minus 1 equals 2 times d of n minus 2. Yeah. Then we replace this d of n minus by 2 times d of n minus 2. So we get 2 squared times d of n minus 2. We keep doing this, and eventually we get to the end. But there is one question here. How do you keep track of all the steps, all the intermediate steps? How do you keep track of them? It's hard, right? We have a method I talked about before, invariant method. Using some invariant quantity, some number, invariant. You use that to keep track of the change in the middle. How to get that invariant number? Look at the exponent of power of 2. Here, 2 to the first plus the size n minus 1, that's n, right? So 1 plus n minus 1, that's n, right? Look at here, 2 exponent of power of 2 plus the size number 2 plus n minus 2, also 2. Is this this n number invariant? When you do the change, you add those two numbers. They are always n. That's the invariant. So we use that to keep track of the, formula change in the middle. So at the end, we have this 2 to the n minus 1, d of 1. 1 plus that n minus 1, also n. So using this way, we are sure this expression should be correct. Okay? Then d of 1 equals 2, so we multiply by 2, so we get d of n equals 2 to the n. Then when we go back to c of n, we get c of n equals 2 to the n minus 1. So that is the solution. We solve it. Yeah. So look at the whole solution, the thinking procedure in our solution. Yeah. All right, so we finish all 3 videos of part A.